After studying this module, you shall be able to learn about the concept of entropy, know the dependence of entropy on temperature in reversible and irreversible expansion, know the effect of variation of temperature, pressure and volume on entropy, calculate the change in entropy in isothermal, isochoric and isobaric processes. Learn about the relationship between entropy and thermodynamic probability. Now we shall see the concept of entropy. The concept of entropy is vital for thermodynamics. The concept of temperature was used in 0th law of thermodynamics, while the concept of internal energy was used in the 1st law of thermodynamics. These are state variables which define the state of the system. The state variable which is related to the 2nd law of thermodynamics is entropy, abbreviated as S. The concept of entropy was introduced by Clausius in 1865. It is considered as the degree of randomness or disorderedness in a molecular system. More the randomness, larger is the value of entropy. The word entropy has been made from energy, En, and trope, tropy, which is for chaos. According to one of the statements of 2nd law of thermodynamics, heat cannot be completely converted into work. This has been attributed to entropy. In thermodynamics, entropy is referred as the measure of the number of definite realizations or microstates that may realize a thermodynamic system in a specified state defined by macroscopic variables. More precisely, the entropy is considered as a measure of molecular disorder within a macroscopic system. The 2nd law of thermodynamics states that entropy of an isolated system never decreases. This kind of system spontaneously moves towards state with maximum entropy, that is a thermodynamic equilibrium. The system which is not isolated may lose entropy only when the entropy of environment is increased by the same amount. As entropy is a state function, therefore the change in entropy of the system will remain constant for any process with the known initial and final states. The change in entropy does not depend upon the nature of the process, that is, whether the process is reversible or irreversible. But the irreversible processes raise the combined entropy of the system and its environment. As on increasing the temperature of the system, kinetic energy of the molecules increases. Therefore, the degree of randomness increases, thereby increasing the entropy of the system. Now we shall look at the mathematical form of entropy. The change in entropy is defined as given by equation ds equals to dq reversible by t. In the expression, Q is the heat transfer considered only during the reversible process, while the entropy change for an irreversible process is not related to the heat transfer during an irreversible process. Q is a path function. It can be shown that entropy is a state function. For finite change and at constant temperature conditions, ds becomes delta S and dq becomes Q. Thus, equation 1 becomes delta S equals to Q by T. Since entropy is a state function, thus change in entropy for change of state from A and B will be same whether the change is reversible or not. Mathematically, the above equation may be written as delta S integration from A to B dq by T. This equation is valid only when the reversible change is brought. Thus, we can write delta S equals to Q reversible by T. Now, we shall see the units of entropy. Since change in entropy is given by ds equals to dq reversible by T, that is heat term divided by the absolute temperature, thus SI unit of entropy is given by joules per degree Kelvin. For molar entropy, the unit is joules per Kelvin per mole. Now we shall look at some characteristics of entropy. Entropy is referred to as the degree of randomness. As the degree of randomness increases, the entropy of the system increases. Entropy can also be related to the unavailable energy. For a given substance, the vapor phase has the maximum randomness and the solid phase has least randomness. Therefore, S vapor is greater than S liquid is greater than S solid. Entropy is a state function. Therefore, delta S is equal to S final minus S initial, which can be further written as S2 minus S1. It depends upon temperature, pressure, volume and amount. Entropy is an extensive property. ds is not equal to dq irreversible by T. Entropy increases with increase in temperature. The entropy increases as the volume of the system increases. Now we shall find the change in entropy in different processes. First, we shall look at the change in entropy in an isothermal expansion of an ideal gas. When an ideal gas is expanded isothermally and reversibly, then the internal energy does not change. That is, delta U is equal to 0. Thus, from the first law of thermodynamics, that is delta U equals to Q plus W, we get Q reversible is equal to minus W equals to P dV equals to nRT dV by V. Thus, change in entropy will be given by delta S is equal to integral V1 to V2 Q reversible by T. This is our equation 6. Or we can write this in the form of equation 7 as integral V1 to V2 nR dV by V, which can be further simplified as delta S is equal to nR ln V2 by V1. This is our equation 8. Now we shall see the entropy change in reversible and irreversible processes. Suppose an ideal gas is expanded isothermally in vacuum, keeping temperature to be constant. This process will proceed irreversibly. As no opposing force is applied, therefore the work done W by the system will be 0. As temperature is kept constant, thus the change in internal energy will also be 0. According to the first law equation, then Q is equal to 0, that is, no heat is exchanged between the system and the surroundings during the process. Thus, the entropy of the surroundings does not change. The entropy of the system is defined by the state of the system, that is, temperature and pressure or volume. During this process, let the volume change from V1 to V2. Therefore, the increase in entropy is given by, for 1 mole of a gas, given by delta S is equal to R ln V2 by V1. This is our equation 9. Or for n moles of an ideal gas, we have delta S equals to nR ln V2 by V1. Thus, the total increase in entropy of the system and its surroundings during the isothermal expansion is R ln V2 by V1 plus 0, which is equal to R ln V2 by V1. This is our equation 10. As V2 is greater than V1, thus we can say that there is an increase in entropy of the system and the surroundings during the irreversible isothermal expansion. Now considering the reversible isothermal expansion of an ideal gas at the temperature T. Suppose the volume changes from V1 to V2 during infinitesimally slow expansion. Expansion is done such that the pressure on the frictionless piston remains always less than that of the gas by an infinitesimal small amount. Therefore, some work is done by the system, that is, W is equals to minus P delta V. Thus, at this temperature T, equivalent amount of heat is absorbed by the system. Accordingly, the increase in entropy is given by Q reversible by T. Similarly, entropy of the surroundings decrease by Q reversible by T. Conventionally, applying the negative sign for decrease of entropy and positive for the increase of entropy, thus the net entropy change of the system and the surroundings is given by Q reversible by T minus Q reversible by T, which is equal to 0. This is our equation 11. Thus, total entropy change during isothermal expansion of a gas is 0. Let us see the conclusion. During an irreversible isothermal expansion, there is always an increase in the entropy of the system and the surroundings taken together. While during the reversible isothermal expansion, the entropy of the system and the surroundings remains the same. This can be written as delta S system plus delta S surroundings is equal to 0 for a reversible process, and delta S system plus delta S surroundings is greater than 0 for an irreversible process. Or the combination of these two above equations can be written in the form of equation 12 as delta S system plus delta S surroundings is greater than equal to 0, in which equal to sign stands for the reversible process and the greater than sign stands for the irreversible process. Thus, the equation helps in determining whether the process occurs spontaneously or not. Since all the naturally occurring processes are spontaneous in nature, thus we can say that the entropy of the universe increases continuously. This statement is also regarded as another statement of the second law. The combination of first law and second law of thermodynamics is given by Clausius, which is the energy of the universe remains the same while the entropy of the universe increases continuously towards the maximum. Now we shall see the entropy change of an ideal gas due to variation in pressure, volume and temperature. Entropy of the system depends on the state of the system, that is on temperature, pressure and volume. For a pure gaseous substance, the value of entropy is dependent only on two of the three variables P, V and T. Generally, T is taken as one of the variable, therefore two variables to be considered are either T and V or T and P. Let us see case 1, when the two variables are T and V. An infinitesimal small change in entropy is given by ds is equal to dq reversible by T. This is our equation 13, where dq reversible is the infinitesimal amount of heat absorbed by the system at temperature T. According to the first law of thermodynamics, delta U is equal to Q plus W. We get dq reversible equals to du minus dw. This is our equation 14. If the work is done due to expansion of the gas, then infinitesimal change in volume will be given by minus dw is equal to p dv. This is our equation 15. Also, we have Cv equals to du by dt at constant volume as our equation 16. Substituting equation 15 and 16 in equation 14, we get dq reversible is equal to Cv dt plus P dV as our equation 17. Assuming the gas to be ideal, thus applying ideal gas equation in equation 17, for 1 mole of a gas we get dq reversible is equal to Cv dt plus RT dV by V. This is our equation 18. On rearranging the above equation, we get dq reversible by T equals to ds, which can be further written as Cv dt by T plus R dV by V as our equation 19. Therefore, the entropy change for finite change of state of the system is given by delta S equals to S2 minus S1 equals to Cv integration from T1 to T2 of dt by T plus R integration V1 to V2 dV by V. This is our equation 20. In the above equation, integration is done between the initial state 1 and the final state 2, and Cv is assumed to be constant within the temperature range T1 to T2. After integration, we get equation 21 as delta S is equals to Cv ln T2 by T1 plus R ln V2 by V1. Similarly, the change in entropy for n moles of the gas is given by delta S equals to n Cv ln T2 by T1 plus nR ln V2 by V1. This is our equation 22. Thus, from the above equation, it is evident that the change in entropy depends on the initial and final volume and temperature of the system. Now, we shall have a look at the case 2 when the two variables are temperature and pressure. Let the pressure of the gas at initial and final state of an ideal gas be P1 and P2 respectively. Thus, accordingly, at the initial state, we have P1 V1 equals to R T1, equation 23, and at the final state, we have P2 V2 equals to R T2 as our equation 24. Dividing equation 24 by 23, we get V2 by V1 is equal to P1 T2 divided by P2 T1. This is our equation 25. Substituting in equation 20 for 1 mole of the gas, we get delta S is equal to Cv ln T2 by T1 plus R ln T2 by T1 minus R ln P2 by P1. This is our equation 26. Since Cp minus Cv is equals to R, substituting this in the above equation, we get delta S equals to Cp ln T2 by T1 minus R ln P2 by P1. This is our equation 27. Similarly, for n moles of the ideal gas, we have delta S equals to Ncp ln T2 by T1 minus nR ln P2 by P1. This is our equation 28. Thus, from the above equation, it is evident that the change in entropy of an ideal gas depends upon initial and final pressure as well as initial and final temperature. Now, we shall see the change in entropy of an ideal gas in different processes. Considering 3 different processes, that is isothermal processes, isobaric processes and isochoric processes. We shall consider each process in detail. Isothermal process. Since in an isothermal process, the temperature remains constant, thus from equation 21 and 27, we get delta S equals to R ln V2 by V1, which is equal to minus R ln P2 by P1, which can be further written as R ln P1 by P2. This is our equation 29. The subscript T indicates that the temperature of an ideal gas does not change during the process. If V2 is greater than V1, in that case, the change in entropy will be positive. Thus, during isothermal expansion, the entropy of the system increases, while during isothermal compression, the entropy of the system decreases. Isobaric process. During this process, the pressure of the system remains constant. Accordingly, P1 is equals to P2. Thus, equation 27 changes to delta Sp equals to Cp ln T2 by T1. This is our equation 30. Subscript P is indicating that the pressure of the system remains constant. Thus, from equation 30, we can say that on increasing the temperature of an ideal gas, entropy of an ideal gas increases. Isochoric process. During this process, the volume of the gas remains constant. Accordingly, V1 is equal to V2. Applying this, the equation 21 turns to delta Sv is equal to Cv ln T2 by T1. This is our equation 31. Thus, from the equation, it is evident that on increasing the temperature of the gas, entropy of the gas increases. Now, we shall see the entropy of mixing. Entropy of mixing can be defined as the difference between the entropy of the mixture of gases and the sum of the entropies of the individual gases which are at pressure P. Thus, we have delta S mixing is equal to, or this can be written in the form of equation 33 as delta S mixing is equals to minus R summation n ln chi, which is equals to minus R into n1 ln chi 1 plus n2 ln chi 2 plus n3 ln chi 3 plus so on. This is our equation 33, or it can be simplified as minus R into summation ni ln chi I as our equation 34, where Ni stands for the number of moles and chi I stand for the mole fraction of each constituent of the mixture. Total number of moles is given by N equals to N1 plus N2 plus N3 plus so on. Dividing this equation by N, we get equation as 1 equals to N1 by N plus N2 by N plus N3 by N plus so on, which is equal to chi 1 plus chi 2 plus chi 3 plus so on equals to summation chi I. Thus, for 1 mole of the mixture, the entropy of mixing is given by delta S mixing is equals to minus R summation chi I ln chi I as our equation. As chi I is the mole fraction, thus entropy of mixing is always positive. Now we shall see the physical significance of entropy. Entropy as a measure of the disorder of the system. All the spontaneous processes occur with an increase in randomness of the system. Such spontaneous processes include flow of electricity, solute diffusion from concentrated to dilute solution, expansion of gas in vacuum, etc. Thus, in spontaneous process, entropy as well as disorder of the system increases. Similarly, in the melting of solid, the entropy of the system increases. This is because the solid has a definite crystal lattice in which atoms or molecules are arranged in a definite order, while in a liquid, order is much less, thereby increasing the disorder. Thus, entropy is referred to as the measure of disorder of the system. Entropy as a measure of probability. In spontaneous process, the less probable state is converted into more probable state. Therefore, entropy can also be related to the thermodynamic probability W of the particular state of the system. Both entropy and thermodynamic probability are directly proportional. This relationship was given by Boltzmann as S equals to K ln W plus constant as our equation, where K stands for the Boltzmann constant, which is equal to R by Na. Boltzmann also regarded the thermodynamic probability as the ratio of the probability of the actual state to the probability of the state in which there is complete order for the same energy and volume. But according to Planck, the constant term in equation 38 is 0. Hence, we get equation 39 as S equals to K ln W. This equation is called as Boltzmann entropy equation. Thus, a solid is regarded as a most ordered state at absolute zero temperature. This implies that thermodynamic probability should be unity, thus making entropy equal to 0, that is S0 is equal to 0. Accordingly, the entropy of all crystalline solids at absolute zero temperature is taken to be 0. Now we shall see a question. Explain the concept of entropy and discuss the nature of change in entropy for the following. Number 1. H2O liquid to H2O solid. The solution is as follows. The entropy will decrease because solids have smaller number of random molecules. Number 2. Magnesium carbonate solid decomposing to magnesium oxide solid plus carbon dioxide gases. Here, the entropy will increase because a substance in gaseous state is formed which has a greater degree of randomness. Number 3. Twice SO2 gaseous plus O2 gas gives twice SO3 gas. Entropy decreases because the total number of molecules decrease. Another question, the enthalpy change for the transition of liquid water to steam is given by delta H vaporization is equal to 40.8 kilojoules per mole at 374 Kelvin. Calculate the entropy change for the process. The solution is as follows. For the given process, water liquid to water vapor, delta S vaporization is given by delta H vaporization by T, which is 40.8 kilojoules per mole divided by 373 Kelvin, or delta S vaporization is equal to 109 joules per Kelvin per mole. Since delta S vaporization is greater than 0, there is increase in the randomness of the system. Question 3. Calculate the entropy change when 1 mole of an ideal gas expands reversibly from an initial volume of 1 decimeter cube to final volume of 10 decimeter cube at a constant temperature of 298 Kelvin. The solution is as follows. Delta S is equals to nR ln V2 by V1, which is equal to 2.303 nR log V2 by V1. Substituting n equals to 1, V1 equals to 1 decimeter cube and V2 equals to 10 decimeter cube, we get delta S equals to R ln 10 or 2.303 R log 10. Solving for this, we get delta S equals to 19.15 joules per Kelvin per mole. Now, we shall summarize what we have learnt in this module. The concept of entropy was introduced by Clausius in 1865. It is considered as the degree of randomness, also referred as disorder of a system. The change in entropy is defined as ds equals to dq reversible by T. SI unit of entropy is given by joules per degree Kelvin. Entropy is a state function, therefore delta S is equals to S final minus S initial, which is equal to S2 minus S1. Entropy depends on temperature, pressure and amount of a substance. Entropy is an extensive property. During an irreversible isothermal expansion, there is always an increase in the entropy of the system and surroundings taken together, while during a reversible isothermal expansion, the entropy of the system and surroundings remains the same. This can be written as delta S system plus delta S surroundings equals to 0 for reversible process, and delta S system plus delta S surroundings is greater than 0 for the irreversible process. During isothermal process, the change in entropy is given by delta S T equals to R ln V2 by V1, which is equal to minus R ln P2 by P1, which is equal to R ln P1 by P2. During isobaric process, the change in entropy is given by delta Sp equals to Cp ln T2 by T1. During isochoric process, the change in entropy is given by delta Sv equals to Cv ln T2 by T1.